Welcome everyone to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension. And on behalf of those folks and our other co-organizers, Wisconsin Public Television, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce to you Emily Ward. She's an assistant professor in the Department of Psychology here. She was born in Santa Cruz, California, and went to high school at Pacific Collegiate School in Santa Cruz. And then she did her undergraduate degree in neuroscience at Franklin Marshall in Lancaster, Pennsylvania. Then she went to Yale to get her master's and her PhD in psychology. And she did a postdoc at the Donders Institute in Nijmegen in the Netherlands. And then she came to the UW-Madison here in the Department of Psychology in 2017. Tonight, she's going to talk with us about seeing and not seeing, investigating visual awareness. Let's see what she has to say. Look forward to hearing this. Please join me in welcoming Emily Ward to Wednesday Night Live.
Thank you all for coming out. I'm very excited to be here. This is my first time as part of this series, and I'm excited to talk about some of my research. So, as a psychologist, I'm interested in the mind. And in particular, I'm interested in the relationship between the mind and the world. How does everything that's out here get into the mind? And the first step in understanding the relationship between the mind and the world is understanding how we become aware of the world to begin with. This may seem very straightforward. After all, we walk around every day, seeing things, noticing things. So this may seem like a weird type of topic to study. But what I hope to show in this talk is that this relationship between the mind and the world is governed by our awareness, and that what we become aware of is not as straightforward and can be very counterintuitive and interesting in many ways that you might not ordinarily think about. So to motivate my research, I want to present an example that I hope not too many of you have experienced, to give you a sense of how there is a dissociation between what goes on in the world and our awareness of it. And that example is a car crash. So just to put what you just saw in perspective, make it a little bit more concrete, this is a timeline of what went on in that previous film. At 0 milliseconds, the external object hits the car. The events unfold such that at about 27 milliseconds, the impact velocity is halved, the airbag is starting to control its deflation, so on and so forth. At 70 milliseconds, the airbag continues to deflate and the occupant moves back to the middle of the car. And what's interesting is that at this point, at 70 milliseconds, this is what engineers would say is a completed car crash. And so one thing that might be missing for you in this picture is that it's not until 150 to 300 milliseconds after the initial impact of the car that the occupant even becomes aware that a crash has occurred in the first place. And I like this example because it gives you an idea of this dissociation between the mind and the world. And some of my research has been focusing on that dissociation. In particular, looking at spectacular examples where we fail to become aware of things in the first place. So in the course of this talk, I hope to convince you of 3 things. The first is that you don't see as much as you think you see. The second is that what you do see can be surprisingly sophisticated and counterintuitive. And finally, I'll end with something a little fun, talking about how your awareness can be altered by information that you don't even know exists in the first place. So a car crash is a little grim to start out a talk with, so I'd like to give another example of how your sense of what you can be aware of is a little different than maybe what you think it is. So there's no task in this part. You guys can just watch this video.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master's bedroom.
I was buttering his lordship's scones below stairs, sir.
I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
But how did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. It's just a matter of observation. The real question is, how observant were you?
Anybody? We'll see this again.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
But I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
So, obviously, I'm giving a talk about visual awareness, and I'm sure some of you were a little skeptical that this would be a straightforward movie, and we're looking for particular changes. But even if you did notice some of the changes, I bet none of you noticed 21 of these changes. Even though when you see it after the fact, these are pretty big changes. These are entire people changing. These are entire paintings changing. There's nothing very small about these types of changes. And so what happened here was that you collectively experienced what I'm going to call a failure of awareness. This is failing to notice something that's otherwise pretty noticeable in the environment if you were paying attention to it. And some of you are probably familiar with some of the most famous cases of this. Whenever you're talking about failures of awareness, most people out in the world, probably most people in this audience, most incoming psychology students, are aware of a particular example, which is more commonly known as the gorilla experiment. This experiment was made famous by a group in the mid-90s, and what happens in this is that there is a group playing basketball, and you as a participant would be paying attention to a subset of the number of players. So for example, you might be paying attention to how often the white players pass a ball back and forth. Meanwhile, in the middle of your task, which is pretty difficult, keeping track of the basketball with only the subset of these players in white t-shirts, a man in a gorilla suit walks through the middle of the display. Most people don't notice this the first time they see it. If you guys are familiar with this, and this is why I don't use this, is you do see it. Once you're aware of it, you have an expectation about what's going to happen, and it undermines this effect. But this effect has been called inattentional blindness, that you're blind to things that you would otherwise notice because your attention is engaged. But despite how famous this example is, there's still a fundamental question about what the nature of this deficit actually is. Is it, in fact, a type of blindness, as the name suggests? Meaning that this is a failure of perception, that you really just don't see that gorilla as it passes through the basketball game. Or is it something a little bit different? Is it a failure of your memory? And what I mean by a failure of memory isn't just that you forget where you put your keys in the morning. It's something a little bit more subtle. And so to give you an idea of what exactly I mean by a failure of memory, I'm going to have you watch another little video. In this video, this is what's known as a rapid serial visual presentation display, RSVP for short. That's not important. What is important is you're going to see a bunch of letters. They're going to be presented very quickly at the center of the screen, and I just want you to pay attention to them as best you can. All right. Can anybody tell me exactly which letters you saw in order? You can't, right? I can't. I've seen this a lot and I still can't. But you wouldn't say you didn't see them in the moment. If it was anything like my impression, is that you have this fleeting sense of what you see, and then it's gone. So that's what I mean by a failure of memory. That simply because you can't tell me what you saw after the fact doesn't mean you didn't see it in the first place. Let me contrast that with the typical story about inattentional blindness, where I'm looking specifically at what you can tell me about it, what you expect, and what I can infer about your experience. So in the inattentional case, you don't have any instruction to report what you're going to see. You have a task that's keeping your attention, but nothing else. As a result, you have no expectation of what's going on. And your then experience is that you're unable to report what was present. Contrasting that with what I just showed you with the letters, a memory deficit gives a very similar account. Except that if I wanted to test whether or not you really saw a particular letter, I would tell you to beforehand clap if you saw the letter M, or the letter A, I think is my example here. So if I give you that instruction to clap when you see an A, you then expect that you may or may not see an A, and then you can tell me if you saw it or not. And so this is how I would rule out whether or not you failed to see or saw a particular letter in the letter display. Can I apply this same logic to an inattentional blindness case? So for example, if I gave you the instruction to report if you saw anything unusual, you would then expect something unusual. And in that case, you can report whether or not you saw something unusual, like a gorilla, for example. But because you were expecting it, that would rule out the effect to begin with. So the very thing that I'm interested in measuring, just by telling you that it might happen, undermines inattentional blindness. And so you can see that getting around this experimentally is a little tricky. How do you figure out if people are really blind to a gorilla, or if they're just failing to report in the same way that you all fail to report the stream of letters? So just to highlight, disentangling this idea that this effect might be a failure to see, or just a failure to remember, is a bit of a catch-22. And I think I might have a way around this. And so I'm going to tell you about a minor change that I made to this logic to see if I can figure out what the true nature of this effect really is. So what I did in this particular study is, instead of giving you no report and having you have no expectation, I wanted to see if I can manipulate your expectation. So instead of having no expectation whatsoever, I wanted to have you expect something unusual, but expect only a very particular type of unusual event. And this, I hoped, would be something that would allow me to see whether or not people could report the presence of something unusual, but maybe would still fail to see something that violated that expectation. So because these types of experiments are very famous, and I can't show people gorillas out in the wild, for example, we use a different type of display. And so again, we're using simple letters in this, and I'll give you a sense of what this looks like. But what we show participants in these types of studies is a computer display where there's a bunch of letters. Some of them are T's, some of them are L's, some of them are white, some of them are black, and they're moving around randomly on the display. And subject's task is to count how many times a subset of them, so in this example it's the white L's, cross that middle line. So every time they cross that, you have to keep track of that. So if you want to give this a shot, I'll show you what a typical trial looks like. Any numbers? 5. All right, you guys are doing great. So it's not impossible, but it's tricky. You have to pay attention. And so because this is a talk, and I'm talking about inattentional blindness, I am allowing you guys to know that something might have happened. Nothing happened on this one, but when I showed this to subjects in the lab, I had another trial, which is similar, except now something slightly different occurred. How many of you noticed that there was a gray cross that went along the middle of the screen? And how many of you noticed the gorilla? All right. So hopefully, for some of you, you still may have missed that cross. This does work particularly well, but there was a slow gray cross that was on the screen for about 5 to 10 seconds. It's right where you're paying attention, so I'm not trying to trick you by having it appear in some peripheral location. This is the type of unexpected event that I used in this study. And so how a typical experiment goes is that participants will see about 4 trials or so where only the letters are being presented, and so that gets them used to the task. And then on the 4th trial, a red cross appeared in this, and so it looked something like this. This is a typical way of studying inattentional blindness, and what you then would ask is, did you notice anything different? And then ask specifically, did you notice if a red cross appeared? And if a participant said that they didn't notice anything and they didn't notice a red cross, I would categorize this as them being inattentionally blind in this case. Typically, about 50 or 60% of people miss this type of cross. Previous experiments have stopped here, but I decided to keep going. And I gave people the instruction that anytime you see anything different or unexpected, immediately press the space bar and we'll ask you to identify it. So this is giving them the instruction to immediately report what they see in the moment. Then I continued on with the trial structure. There was a few more trials where nothing happened, but importantly, there was a few more trials where the red cross appeared. So they were building up this expectation that there might be something unusual, but that unusual event was the presence of a red cross. Importantly, at the very last trial, there was a critical trial where half of the subjects saw a new event. In this case, it was a blue E moving the opposite direction on the screen, or just another instance of the red cross moving across the screen. And the question is, if people are presented with something that violates their expectation about what's going to occur, do more people miss this new unexpected event compared to just another instance of the repeated unexpected event? So I'm going to show some data that answers this question. So here I'm plotting the percent of people who miss the unexpected event on this critical trial by what type of event it was. Was it the new one or just the repeated one? So first of all, I measured how many people missed this repeated event. A few people, while they were doing the counting task, did miss it, but it's not very many. Critically, almost 5 times the amount of people missed this new unexpected event. So this means that more people are missing that event even when they're given that instruction and even when they're willing to respond immediately to what they see on the screen. So what this means is that you don't see as much as you think you see, and that this phenomenon of attentional blindness arises specifically due to you having the wrong expectation about what's going to occur out in the world. And that this phenomena also reflects the limitation of perception and not of your memory. So this has implications for the real world. This means that if you are driving while distracted and a child runs out in front of your car and you hit it, that's not because you saw it and then forgot in the way you would see these letters that I had presented earlier and forgot. It's truly reflecting a limitation of your perception because your attention is otherwise engaged. So this is a good example of how limited what we see can be, but it stands in contrast to what we think our daily experience actually is. So why does it seem like we see so much when I demonstrated just now that our experience is limited by these limitations in perception? So I'm going to show another video right now. No task. Just sit back and take this in. So just like before, if I were to ask you what exactly you saw in order, you probably wouldn't be able to tell me. You can recognize these types of scenes very, very quickly if you know what's going on beforehand, but also if you don't know what's going on beforehand. And it also just strikes you as really rich. You see a lot of detail. You see exactly what's going on. These pictures seem evocative. They seem beautiful. They seem interesting. And you can do all this even though this is presented very quickly. So this is in contrast to what I just showed you, where we can be really bad at seeing noticeable events or changes out in the world. But we also feel like we're really good at noticing rich detail. How do we reconcile these two experiences? Is it that we have a limited awareness of detail, but we are instead aware of some statistical properties of the world that make our experience seem so rich? So I'll unpack that a little bit. I teach statistics here, so I know when I mention that, a lot of people's eyes glaze over, and they think this is what I'm going to be talking about. That's not really what I mean in this particular case. Even in general, it's not really what I mean. What I'm talking about is, do we perceive statistical properties? And so what that means is that if I put up a display like this and give you guys the task right now to tell me what side, right or left, has the biggest average size circle. Can you tell me which one you would guess?
Left.
All right. Average is a statistical property. So here, you're doing some computation over all of these elements and telling me that you can see that this left side contains a bigger average size. I'm going to give you another one. This one's going to be a little bit trickier, and I'm also not going to present it for very long. So again, which side, right or left, has the bigger average size circle? Right. Okay. You guys are doing great. So that's completely true. And what's interesting about what you just did is those were only presented for about, I think, a second or so. So it's enough time to do a lot of processing, but it's not a whole lot of time to make a cognitive decision about it. And what's interesting in this case is that you also were able to discount the largest circle. So the largest circle of all of these circles was actually on the left side. But on average, you're discounting that and just taking that average statistical property. So you were able to do this statistical calculation, but what if I asked you, was this particular circle in the display? So this is motivating my question. Can we perceive statistical properties without actually being aware of the individual elements that give rise to the statistical properties? So the example I just gave was an average. For those of you who remember statistics, that's not the only important property when you are looking at an array of things. Another one is the diversity or the variance in them. And so here, instead of looking at size, I'm looking at color. So on one side, and I think this works for even those of you who might be colorblind, can anybody tell me the difference between the right and the left here? Yes, exactly. So on the left, this is colors drawn from a low diversity circle on the color wheel. So only sampling from ones from this area. Whereas the ones on the right are drawn from high diversity. I'm taking them from anywhere on this color wheel. And so this is an interesting type of statistic. This is looking at the diversity of a set of things. In particular, looking at the diversity in color. This type of display can also be used for me to figure out what kind of details do people notice. So I can then ask, are people aware of any individual element in these types of displays? Or are you aware of the statistics of this ensemble of dots, for example? And it's hard to do this with shapes like this. So I can do one thing that makes it easy for me to figure out what specific details you know about each individual element. And that's to translate them into letters. I can ask you both then about the colors and about the identity of a particular letter. I can ask you what letter was at that particular position, while also having you pay attention to whether or not the color of the display on whole came from a high diversity or low diversity color space. So this question, just to reiterate, do you perceive ensembles without perceiving the individual elements? How this type of study worked was that I would cue people beforehand to pay attention to a particular row that was going to be displayed. And so even though I'm going to be presenting a lot of letters, your attention is going to be limited to a particular part of the display. Then I'll show the display. This is 300 milliseconds. This is plenty of time to become aware of things. Remember from the beginning, at that point you know your car has crashed. And so it's fast, but you can still do a lot of processing with that type of presentation speed. Then after a blank interval, I will ask you about a particular letter at a particular place. So you tell me what appeared right there. And then I can ask you, what was the color diversity? Was it high or low? And I can ask you that about the letter, or about the row that you were paying attention to, or to the rows that you weren't paying attention to. So, first, letter recall. How good are people at this type of task? So here I'm plotting accuracy. Here chance I think is about 12%. So how good were people? And this is when they're either attending to the color of that row or attending to the color of the non-cued rows. So does splitting your attention for the color task hurt your ability to tell me what a particular letter was? And it does not. People are fantastic at this task. You guys will be surprised. I will show you what this looks like in a little bit. But people are very good at identifying letters, even when these displays are presented for just 300 milliseconds. And splitting your time, or your attention between the two different types of rows, either the cue or non, doesn't hurt your performance. What about color diversity? Here, chance is 50% because it can either be high or low if you're guessing. Again, people are very good at this task. And it doesn't matter if they're paying attention to the color diversity of the cued row or the non-cued row. They're just as good at either of those. So overall, we're back to this story of looking at whether or not people are doing these tasks because they are aware of every single element, or if they are aware of just the ensemble without the elements. Both of these theories have predictions about how good you should be at letter recall and color diversity. So if you're aware of all of the elements, obviously you're going to be good at recalling letters. If you're aware of the ensemble without the elements, you still have some access to some detail. Otherwise, we wouldn't be able to read or recognize people. So both of these predict that you should be good at both of these, at the letter recall. You can do the color diversity task either by having an ensemble statistical processing going on, or because you're processing every single element and then doing the computation that gives you the ability to say whether or not it was high or low diversity. So again, both of these don't make any different distinguishing between these two theories based on this result alone. What I needed was some way to distinguish these. And particularly, I wanted to see whether or not people notice changes to the elements. So if you are aware of everything, if I change anything, you should be aware of that. You should notice that. And so that theory predicts that you would be able to notice changes to the elements. However, if you are aware of an ensemble without perceiving each element, you may not notice changes to any or all of the elements, as long as the statistical properties remain the same. So to manipulate that, I'm going to show you what this display actually looked like. So here, just so that people had enough time to see what the colors were, the display starts with these 0 figures before switching to numbers. And so this is what an actual several trials of this looked like for participants. All right. So it's pretty surprising, but people were very good at this. Was there anything else anybody noticed about these displays besides just that it seems like a very difficult kind of experiment?
The second one changed colors.
All right. They all changed colors, actually. So the cued row didn't, but every other element in this display changed color on every single trial that you just saw. And so maybe some of you are saying, well, come on, that was super fast. There's no way anybody would have noticed those, even in principle. So I'm going to show you it again with a particular type of instruction. So what will help you to see that these are not completely unobvious changes is if you pay attention to a subset of this display. So I want you to try as best as you can to pay attention to both of those positions. Because then regardless of what I cue, one of them will be changing, okay? So you got that? So pay attention to the letters that will appear at both of those positions. All right, so hopefully you were able to notice them much better than you were the first time. It's still tricky. It's not the most obvious change in the world. But the idea is that if you are perceiving every single one of these elements, you should be able to notice at least one of these changes across the experiment. And so I did 2 experiments with this, and they're fairly small in nature, but nobody of the 12 observers in either of these noticed any of these changes. And if you actually do the math on this, there's 18 letters that were changing on every trial. There was 192 trials in which there was a change, and that means there was 3,456 possible changes for you to notice. So that nobody noticed any of these really starts to lend support that you are perceiving the color of these displays, the color diversity of these displays, without perceiving the individual elements. So this really supports this idea that we have this sophisticated statistical processing that's going on even when we aren't aware of it at all. So why does it seem that we see so much richness based on the other types of failures of awareness? Well, it could be that we are aware of these types of statistical properties. We're aware of averages, we're aware of variance, and we're not actually processing consciously all the individual details at any given time. And so this gives an account of why it seems like the world is rich while we can still miss critical details in the environment. So finally, I want to end with a fun, smaller experiment trying to see how our conscious experience can be altered and what type of information can alter what our experience is. And particularly asking this question of whether or not our awareness can be altered by information that we aren't aware of at all. So I showed that we aren't aware of a lot, but what kind of functional role does that play in governing our moment-to-moment experience? So there's particular examples that I'm sure you guys have had a lot of exposure to, even if you don't study vision like I do. In particular are these types of images, ambiguous images. This one's called a Necker cube. And what you are probably doing right now is paying attention to different aspects of this cube. And depending on where your attention is, you can see it in one of 2 interpretations. You can either see it as going away from you, or you can see it as coming towards you. Sometimes you can do this willingly, but a lot of times it just seems kind of random. It seems like what you're experiencing is just driven by something that you don't have any control over, and you see the alternations between these two types of interpretations of this cube without having any conscious control over it. So this is a famous example that's used in a lot of different types of studies, but there's also examples of these types of ambiguous images out in the wild. And one that you might have seen, it got famous on the internet a little while ago, is one that looks like this. So I think this should work. So this is a dancer that is ambiguous in depth. She is just a silhouette, so you don't get any depth information. And as a result, your brain really doesn't know which way she's turning. But you can't see both interpretations, left or right turn, at any time, and so your brain makes a decision about what you see. So how many of you see her going clockwise? All right. Counterclockwise? How about anyone who's seen it flip back and forth? All right. So most people will see her going clockwise. That's a predominant way that this is interpreted. There's a couple of different reasons for that. One is that her foot is angled a little funny. And one interpretation, I think counterclockwise, your brain would have to decide that you're looking at her foot from below, which is a weird way to look at feet. So it's also dictated by how fast she's going. There's a lot of different things that you can do to manipulate it. But the idea is this can go both ways. And so just to make that clear for those of you who weren't able to see her going both ways, if I put a cue on her that helps you see her, so this effectively disambiguates her direction. This takes that ambiguous information about her depth, and by putting eyes on her, makes it so that she has to be going one direction. So on the right here, she's going clockwise. And hopefully if you pay attention to her face, that might help. And here, she's going counterclockwise. And what's fun about this one is because clockwise is so strong for a lot of people, her body can start to look like it's doing some very funny things. And then again, there is this ambiguous interpretation in the middle where it could go either way. My question was, can we make you switch your perception of her direction? And in particular, even if you're not aware that we're making you switch. And so how this worked was that I showed you one version of the disambiguated figure, which again tells you that she has to be going one way or the other by putting eyes on her. Another way to do that is to put very subtle contour cues on other parts of her body, in particular her legs. So for example, here is exactly the same frame from the animation, but it has different contour cues. So this one indicates that her leg has to be facing forward. The other one indicates that her leg has to be facing backwards. And so by putting these types of contour information, it is telling your brain that there is a correct interpretation of an otherwise ambiguous figure. And so the idea was, can we introduce these types of cues to people and have them basically forcibly have their perception of her direction be switched, even when people don't notice these cues were there at all? So to you guys, it just looks like a continuous movie, as it did to the participants in this experiment, but of course it can be broken down into individual movie frames. And so the idea was we had people come in and they had the task of pressing the left or right arrow key to indicate which direction they thought she was spinning. And so this was a fairly boring experiment for subjects who believed they were watching this spinning dancer for about 45 minutes, pressing a button one way or the other. Unbeknownst to them, on certain frames of this, we would introduce one of these disambiguating contour cues. We would have a cue, and then the idea would be to measure, do people switch shortly thereafter, having seen this, having been presented with this cue, but not necessarily noticing it or seeing it? And so again, because we're interested in whether or not we can make you switch, even if you're not aware of it, we only included people who said that they never saw any of these contour cues. After the fact, we always talk to the subjects about what they think the experiment was about, what their experience was. And so in this, anybody who saw them, we didn't include. We only included people who said they had no idea that there was anything like that present at any of that 45 minutes. So to measure this, we would have the whole segment of the movie broken up into frame segments. We would have a cue presented, and then we would look for a switch that happened after the cue. This could be a fairly short time period after. It could be at a different point in the different frames. We could measure the reaction time there after presenting the cue, or we could look at a much longer duration. The idea was that any time after presenting the cue, if people are switching above what they do just by baseline, that would mean that something that we're presenting unconsciously to subjects is influencing what they see. So, to make sure that we have captured this, we can take all of the time points where a cue was presented and line them up, and then basically count how many frames after that produced a direction switch. So does that make sense? We're basically time locking the whole thing to the presentation of these unconscious contour cues. So I'm going to show here the amount of switching above a baseline that we measured for each subject, because some people, unfortunately, sat in there the whole time and didn't see it switching direction once. And so on the X is how much time passed after the presentation, and on the Y is the amount of switching that occurred. And so what you see is that in the first second or two after presenting these cues, the unnoticed contour cues caused people's perception of the dancer's direction to switch. And so this means that even though they didn't notice it and they thought their behavior was just random, we were actually causing their behavior to change. So can awareness be altered by information that you don't even know exists? Yes, it can. What you experience can be governed by awareness, by information that you had no awareness of whatsoever. And also another thing that's interesting about this experiment is that the feeling of randomness that you may have just going through your daily life doesn't necessarily mean that there isn't systematic processing going on unconsciously in visual perception. Your brain was interpreting these cues in a way that made sense. It wasn't just randomly having these direction changes. It was interpreting them even though you weren't aware of it. So overall, I hope that I've convinced you that you don't see as much as you think you see, and that what you do see can be much more sophisticated than you may realize, and that your awareness and your everyday moment-to-moment experience of the world can be governed by information that you don't even know exists. So overall, how the world gets into the mind is governed by this process of becoming aware of it in the first place. And hopefully now you all have a little bit more appreciation for how sophisticated and counterintuitive and interesting this process is. Thank you. And I'm happy to take any questions. Yes?
Can you talk about how your awareness is influenced by cues in social media that you're not aware of?
I think that a lot of times I get similar. So the question is, how is your awareness governed by cues that you get on social media that you aren't aware of? This is something that also I've thought about in terms of advertising. A lot of people are somewhat suspicious or worried about subliminal messages. I think these effects are small. They're meaningful in terms of interpreting how the mind works, but in terms of governing huge behavior, what's much more effective is to have not subliminal cues, to just be outright saying something, and that that type of information that you're getting is far more important and potentially damaging, both in terms of making political decisions or buying Coke versus Pepsi. Yes?
Can you actually choose not to see something and really not see it?
Yes. The question was, can you choose not to see something? You can close your eyes and it's gone.
Well,
So there's always that.
maybe there's something you'd rather not see and just...
If there's something that you'd rather not see, if there's a way to not see it. I think it depends a lot on the type of information, the type of picture, type of content that we're talking about. It's beyond the domain of my research, but people are very good at deceiving themselves and coming up with reasons for their beliefs. There's a phenomenon known as, I think, choice blindness, if that's true, where you are, I think, given a series of cards and you choose one, and then as you put it back, it's replaced with a different card. And then you look at it again, and you don't notice that it's changed, and you also confabulate why you chose it. So there's a lot of that kind of much higher level cognitive processing that can go on. But in terms of just perceiving things that you don't want to, at this kind of low level visual level, I'm not confident that there's a way that you can do that. Yes?
What factor does age play in your experiments or in your studies? I'm assuming that older people perform less well at some of these experiments than younger people.
So the question was how age factors into these types of results, these studies. So for some of these studies, I tested only college students, but the study with inattentional blindness, where you're tracking the letters moving across the center of the screen and the X goes one way, that was run online, and so it's open to the world. And so we don't collect demographic information just because it would take more time to do that than it takes to run these studies, which last about a minute. In general, age factors in a couple different ways, but the one that plays the biggest role is that older individuals tend to be worse at tracking the objects. And so if you are not performing as well on that primary task of tracking the white L's, for example, that are moving across, you actually have more attentional resources to notice unexpected things. And so it can go in two different directions. In general, I think that's not usually the case. I think usually inattentional blindness rates are higher in older individuals, but there can be interesting trade-offs based on how well that primary task is performed. Yeah?
What is the effect of experience in looking at these things, learning how to do these better, these chances, and what effect does that have, or have you studied that?
So the question is, what effect does experience and learning have on these? There's a few just anecdotes that I can say about it. For example, that the spinning dancer I looked at for probably hours and hours of my life right now, and I can make her switch whenever I want, as often as I want. And that, I think, is due to the fact that my brain has learned that this particular stimulus is not really reliable. And so the things that it would ordinarily use as reliable information to make an interpretation, like how fast she's spinning, the placement of her foot, like the things that are driving you guys to see it for a while and have it be a sticky kind of phenomena, my just implicit learning of it has it flip back and forth a lot. The other types of learning are ones that can make you do a little bit better. Although I haven't studied it exactly, one question that I've had with the elements versus the ensemble statistics is not in the domain of perception, but if you are a heavy meditator, for example, and you have trained yourself to notice things in the environment and notice things about yourself that other people don't, what effect does that have on whether or not you notice these elemental changes? I think that would be a really interesting question, but I haven't looked at that yet. Yeah.
Have you run any of these types of experiments on autistic people? My understanding is that there's some theory that their problem is they cannot focus. And in fact, they're taking in all this information, and that's what kind of overwhelms them.
Mm-hmm. So the question was if I've run these experiments on autistic people. I haven't run them myself. I know that at least the ones with the inattentional blindness have been run, and I think in general they notice it more. The idea, probably because they're taking in this extra information in the environment typically, although I don't completely know if that's the case. That's what I think is the case with it. But in general, I am interested in just trade-offs among individuals. So for the people, these types of inattentional experiments, you can usually get 40 to 60 people to miss it, depending on how you set up the experiment. But what's interesting is that so far you can't predict who's going to be in that 40 or 60. And so is it the case that these things are just random fluctuations? Is everybody susceptible to these failures of awareness sometimes, or are some people always susceptible to these failures of awareness? It's tricky to measure that because so often it's a one-shot type of experiment that once you have this type of expectation, it undermines the effect. I got it twice. I don't know that I could extend that for too much more in any setting, but looking at it over time might be one way of getting at that question. Yeah?
Can you tell any difference between left-handed and right-handed people?
Differences between left-handed and right-handed individuals in that last experiment or just in general?
The rotating dancer.
I didn't look specifically at that, so I don't know right off if there's any handedness difference for that. Yeah?
How would this change with the children and toddlers whose perceptions haven't been as well trained? You might not be able to run the letters, but you could use other shapes or something.
Right, so the question is how would this be different in children or toddlers who don't have the type of visual experience that adults have? I think that's a great question. It's hard to do. I would love to be able to do that. One issue with running kids is that, again, you usually only have a couple trials with it. And so in the case where they're reporting the letters and the colors, you're dealing with them having to give you two different kind of reports. If they can't understand language, how you get at that is much trickier. But it would be very interesting to see if there's some sort of developmental change. I think the last study with the dancer would probably be the easiest to do. With kids, you could probably find what direction they're looking if you designed it well enough. But even just looking at inattentional blindness with kids, I don't know that people have done it with that young of kids. Usually the ones that they've looked at are ones that are elementary school level. And again, how that changes is that the younger they are, the worse they are at that counting the number of passes or the times the letters cross the line. And as soon as they're just not equated on that primary task, it's hard to make a judgment about what the actual rate of noticing versus not noticing that unexpected event is. Yeah?
I may have missed this. How did you arrive at the interval, the frequency that was meaningful for you? Did that go back to what we learned from the car crash at the beginning, that there's a certain amount of time? Because it seemed as though everything was very, very quick and a couple of many.
So the question was about how I arrived at the timing of a lot of these?
Yeah, I mean, could they be slowed up or
Yep, so in a lot of these cases, they were based on previous studies. And so with the exception of the dancer, these were designs that other labs had done in some form or another. And so I wanted to make sure I could replicate their science as well as extend it to say new things. Typically, you would calibrate something so that you get the type of behavior that you want. If it's too fast and nobody can do it, that's what's called a floor effect, and it's not going to give you that variation. If it's too easy and everybody can do it, that's a ceiling effect, and you're also not going to have much variation. And so having people's performance be better than chance, showing that they can do it, but not too good or too poor, is usually that sweet spot that we're looking for in these kind of psychological studies. It wasn't based on the car crash example. That one is just sort of detection. These are much longer intervals than that typically, but again, it's based on just trying to find variation among people, showing that they can do it, but they're not great at it. Yeah?
you have plans to use an eye tracking setup on your participants?
So the question was looking at eye tracking for these. I've used it for a couple different experiments. I haven't used it for these. One, there's a couple different ways you can use it. You can look at where people are looking, but one exciting method that people are using for studying awareness is looking at pupil dilation and how that tracks what you become aware of or not. And so one line of research that I'm interested in is how things that happen after the fact influence our perception of a moment earlier. So it's a little complicated, but there's a few of these examples where we're sort of continuously integrating information. And eye tracking, especially looking at pupil dilation, might be a way of figuring out if that first experience is updated or if it's some later process in perception that's actually influencing our ability to make decisions and talk about our perception. Yeah?
Is there any reason to think that some of the problems with cognition, like Alzheimer's, that we associate with memory, could instead be due to inattentional blindness?
That's an interesting question. The question was if problems that are typically thought to be higher level cognitive or memory problems, like in Alzheimer's, could be due to attention problems, specifically in more inattentional blindness. I'm not totally sure. I think there are issues both with memory and also the ability to attend to different things. And so I would suspect that that hasn't been looked at super carefully together, that you're usually just doing a memory assessment or an attention test and not looking at how they can be much more related, like I did in this kind of deeper theoretical way. So I wouldn't rule it out, but I don't know specifically. Yeah?
You showed us the car crash in slow motion, and we could see the car crashing and the various steps that happened. But how has it been determined that it takes as long as it does for a person to become aware the car has crashed? Because surely this work wasn't done by crashing cars into
Right. So that would be a hard thing to pass by the university IRB. I think that time that I gave you is dictated both by just the basic reaction time that people can give to detect any kind of event in the environment, and also just by the neurophysiological constraints. How many axons are between sensing something out in the world and getting back to your visual cortex enough to detect it? And so you can't be aware of it before the information has propagated through the neurons. And so that window of 150 to 300 is a pretty big window of time, and I think that's just based on both the raw physiology and also the time it typically takes for anybody to detect anything.
Well, the follow-up question would be, what is the awareness? Because I remember bumping into something at very slow speed, and I could feel I was bumping into something, hitting something, and it took me a while to say, oh, I just crashed it. But there was a physiological awareness of something obstructing, and then it took me a while to realize what happened.
Right. So the question is, when you hit something like that, why is it the case that you sometimes have this dissociation where you know something changed in the environment, but it takes a little bit longer for you to interpret what happened? To name it, yeah. So the question of what awareness is a very complicated one. And so I only touched on a little tiny bit of it, but there's a lot of definitional aspects that I brushed across here. I think in the particular case that you're talking about, there's also just physiological responses that happen, stress responses, and you saw it in the time frame that I set up there, that there's just no way that you could see it any faster. But you also have hormones that are engaged, and just because you can see something, you can have that visual processing going on, doesn't necessarily mean that you're able to name it, that you're able to think about it. And those, especially when you are in a stressful situation and you have stress hormones that are flooding your body as you know you're hitting something, probably cloud your ability to go from visual perception to talking about it, reasoning about it, thinking about it. So I don't have a good answer of what exactly awareness means in these cases. I'm talking about visual awareness, and so being able to see something and say you saw it, or give some kind of report that you say you saw it. But I'm not saying too much about the time frame of it.
And that strikes me that the physiological awareness is quicker than the
Well, I'd say both of those are definitely faster than the analytical process. I don't know enough about how hormones work to know how fast that happens. It feels like it's faster, but again, if you're not specifically pitting those against each other and looking at the actual physiology, it's hard to know exactly which one is winning that race. In the back, yeah.
I noticed the objects are moving. I was thinking about a phenomenon called blind sight, where someone is blind from a stroke, but the fovea still connects directly to the pineal area. And you throw a ball, and these people are stone cold blind, but after a while, they can tell you where it's at. Movement is an issue there, because some people see different. There's also a technique of increasing visual acuity and awareness by rapid eye movement to left and right. Pilots are taught that. Just offering that up.
So the comment was about blind sight and other cases where you can either by having some sort of brain lesion or some sort of experimental manipulation effectively kind of turn up or down the gain on what you're aware of. I think all of those cases are really fascinating, and especially blind sight is a great one where it shows you again that it's not this straightforward link between what you think you see and what you're actually able to act on in the world. And so trying to figure out exactly how rich and how, like, what the nature of conscious visual awareness is a really interesting question. The approach I take is to try and look at the smallest aspect of it, what I can measure in regular people, but the patient population for these kind of cases is super, super fascinating.
If you stop the connection on the fovea and someone who can see, they can't track motion.
If you stop the
track that goes to the pineal gland.
Yeah, I'm not entirely sure about that because we do have a lot of motion in the periphery as well.
And it's also true in different file of animals.
Yes?
You mentioned eye dilation. Have you done any further studies with fMRIs, and does that correlate to cognitive load of the eye dilation?
I don't know if anybody has looked specific. So the eye dilation is a fairly newish technique in terms, at least how it's being used for visual awareness. It's a slow response, at least compared to some other saccades that our eyes make, and so that actually makes it a nice candidate for fMRI, which can measure only sort of slow responses. I've done a lot of fMRI work, but I haven't done it with any of the visual awareness. I'm specifically looking at how people recognize objects and scenes and how that relates to memory. Nothing that requires really fast responses. Yeah?
If you're running some of these online, are you worried about central visual processing with the fovea, the hill of vision, and or you've got different color stimuli? You've got a red cross and a blue. Are you worried about magnocellular or parvocellular receptive fields within the retina, because that will throw this entire thing into disarray?
So the question was, if I'm running it online, what kind of considerations do I have to think about in terms of who I get, basically in terms of what they're paying attention to and what their color vision is. So we always administer a color vision test.
I just meant visual viewing distance, the angles of
Yep, so we have no idea how they are looking at these. What we do have is a series of checks, so they have to be able to tell us what they had to do after the fact. And so if they were reading the instruction, they had to maintain good performance on the primary task. And so if they were able to sit across a room and still count the L's as they cross the midline, then we would include them. The central versus peripheral processing, because they had to pay attention to the center of the screen, the hope is that that minimizes any issues with even just in general peripheral vision being worse at detecting these things. But the benefits to running it online are that we can get 100 of people who don't notice the first unexpected event, whereas previous studies would maybe get 20. And so there's a lot of things that we can't control, but the benefits really, really far outweigh any of the shortcomings.
Another question or two?
Yeah.
Did you have problems with either beforehand, people seeing something because they were expecting to, or afterwards, when through power of suggestion, they remembered seeing it and they actually didn't?
So when we were running these people online, we always asked them if they were familiar with the gorilla experiment, or if they expected something unexpected was going to happen. If they answered yes to either of those, we didn't include them. And so that was one way of minimizing the sort of upfront expectations that they have. There's always a risk that somebody, just by guessing, can guess that they saw the red cross. But that's usually a very low amount of people, but we would have included them in that if they were able to correctly guess in the right way if you had actually seen it or not. Yeah?
Okay, if I understand this correctly with what you were answering some of the questions, were most of the time when you're doing these studies, you're doing directed perception. Is that correct? For the most part, basically, from the way I'm understanding the percentages of response?
So the question is, most of the time people are doing directed perception, meaning that I'm telling them to pay attention to...
For some particular feature?
Yes.
Okay. And if they use a non-directed perception and they have to rely on subconscious imprinting, are you saying it drops down about to 20% of the typical then, which would be, like say if you had a response of 60%, you'd have a 12% response on a subconscious imprint?
What do you mean by subconscious imprinting?
Subconsciously, everybody sees everything that's there, whether they realize it or not. The ability to recall that is determined by the individual, whether it's through whatever technique they use, whether it's meditative or some type of retrieval system that they use personally. Have you studied it within that aspect to see what kind of difference in perception percentage-wise you get compared to a directed perception?
So there's issues when you don't have a task that a lot of people will make a task for themselves. And so then what you get into is you're measuring strategy differences rather than anything that has to do with perception directly. And so the cases where people are free viewing something or they have no idea what's going on, you just have a lot less ability to interpret that. And again, based on what types of details you have in the display, the percentages can be moved around a lot. So if I made that cross that went across much more difficult to see, more of you wouldn't notice it, but not for a very interesting reason. And so you can mess with the absolute percentages, but the idea is you always want to have good comparison groups that you're comparing to. And so in general, even just the case where I had the new object, which was the blue E, I also had the second group where they're getting another exposure to the red thing. So in both cases, I'm trying to equate task because when you have this free, undirected situation, like I think you're talking about, you end up having people just coming up with their own crazy ideas, but it's not really getting at perception or even memory differences in a lot of cases. Yeah.
Have you published these studies and are they on your website?
Yes, every one of these is on my website and they have been published. And you can download them for free.